So potassium nitride, if you're curious about how we got from the name to that formula, see the video or the previous section where I talked about how to get this. Now what we're going to discuss is Lewis structures. So these things always have names after people who came up with these things, and Lewis is the name of the gentleman who came up with this methodology. In order to utilize Lewis structures appropriately, you have to know how to get the valence electrons off of the periodic table. If you consult your periodic table and you look at the groups in the main group elements, another great pattern in the periodic table is group 1A, group 2A, group 3A, all the way out to the noble gases 8A, will tell you the number of valence electrons in their outermost shell. In fact, that's what the valence electrons are. The valence electrons are the outermost electrons in the atom's outermost shell. So that being said, if you look at group 1A, and I encourage you to go to that ptable.com, find out where group 1A is. It's the alkali earth elements. And all of those elements in that entire group, in that entire column, all the way down, I think from hydrogen down to francium, all of those elements have one valence electron in their outermost shell. The second group, group 2A, those guys have 2 electrons in their outermost shell. Then go over to group 3A. Group 3A has 3 electrons. You see the pattern? Let's skip all of these and go out to group 8A. Can you guess how many electrons that group 8A has in its outermost shell? If you said 8, you're correct. It has a full shell of 8 electrons. So the bottom line is, if you know the main group of elements, 1A, 2A, all the way out to 3A, all the way out to 8A, if you know what the main group elements are, then if you look at the periodic table, you'll be able to identify the valence electrons. So what does this have to do with Lewis structures? This has a lot to do with Lewis structures because in chemistry, the most important electrons are the valence electrons. The valence electrons are the ones in the outermost shell. Why is that? Because those are the electrons that participate in chemical reactions. In fact, the valence electrons are the reason why chemical reactions occur in the first place. So we figured out what the molecular formula, right here, what I'm showing in this red box, is the molecular formula for potassium nitride. That's the molecular formula. And what it shows is it shows us what potassium nitride contains. I look at this formula, I know he's got 3 potassium atoms bonded to 1 nitrogen atom. But it doesn't show me the structure, okay, of the atom. Let's start off with Lewis structures. A simple Lewis structure on the element of potassium is as follows. You write the element symbol down first, and then you look up where the element occurs in the periodic table. This guy occurs in group 1A. If he occurs in group 1A, you put the number of electrons that correspond to the group number somewhere on the element name. Now, there's a sort of a convention to this, or a template to this. You can put the electron in that location, you can put the electron in that location, or that location, or that location. In other words, up, down, right, or left. And it doesn't really matter where you put that electron. So what I'm going to do is I'm just going to decide, okay, I like it on the right-hand side, so I'm going to put the electron right there. So when you, now this is not the Lewis structure with the green boxes. I'm just showing you what the possible locations are of where you can put the electron. Now again, potassium does not have more than 1 electron in its valence shell. We could go to calcium. Let's go to calcium. Calcium, the same thing. Imagine the four electrons are surrounding calcium. And just double checking my periodic table, yes, calcium is in fact in group 2A. If it's in group 2A, then calcium has 2 electrons in its outermost shell. Now, given what I just told you, you could put the electron there if you like, and you can put the electron there if you like. Now, some students, what they'll do is when they're drawing the Lewis structures, they'll immediately start pairing up the electrons like this. Don't do that. In other words, write the electrons separately. So the calcium, one valid Lewis structure for calcium could be like this. Another valid structure for calcium could be like this. In other words, resist the urge to pair them up immediately. There's a reason why that's important. Let's go to carbon. If you look up carbon, carbon is in the periodic table that corresponds to 4 valence electrons. Again, resist that urge to pair them up. So in other words, fill up the possibilities or occupy the possibilities with 1 electron first. Carbon. Now I have to consult my periodic table. In the next column over, let's pick on nitrogen. In fact, we're going to use that in our example. Nitrogen is the next group over from carbon. So he has 1 more valence electron than carbon does. So we're going to write it the same way when you initially write it out. Pay attention to the way I'm writing it as carbon. But like I said, nitrogen has 1 more valence electron. He doesn't have 4, he has 5. So where am I going to put that 5th electron? You put it in any one of these 4 possibilities. Pair them up. And with these imaginary green boxes, they have a certain rule that you have to follow. The rule is that the imaginary boxes have a maximum number of electrons that you can put in them of 2. So this is the rule that you follow with the Lewis structures. In other words, if I move to the next element that's next to nitrogen, let me consult my periodic table. That's going to be oxygen. If I do oxygen, then I don't put 3 here, okay? I put another pair there. And that's how you do the Lewis structures. All right, we're not concerned, for our example, we're not concerned with calcium or carbon, so let's erase those. We're only concerned with potassium and nitrogen. And I'm going to erase the little green boxes so I get them out of the way for the moment. Let's just do, and I'll put nitrogen up here next to the potassium. And there's a strategy I have in mind for doing this. Now remember, it's got 5, so I'm going to do 4 initially. And I'm going to put the pair over here. You can put that pair over here or over there if you like. It doesn't really matter. But you're going to see in a moment why I have these 3 single electrons next to this single electron. Now, if I have a potassium, this represents, by the way, a potassium atom. The Lewis structure represents the atoms. This represents the nitrogen atom. It represents the nitrogen atom and the potassium atom, but I can't emphasize more that it also represents the valence electrons. So potassium has 1, nitrogen has 5. Why is this important? This is important because this really gets to the reason why these things bond the way they do. Remember that I showed you with the charges, we're able to get the molecular formula, K3N. But there's another way of looking at this. All right? And it involves something called electronegativities. What is electronegativity? It is not to be confused with the charges of ions. I can't tell you how many students I've had that get confused between the charges of ions, you know, +1 or -1 or +3, and they think that that is electronegativity. That has nothing to do with electronegativity. Electronegativity is the affinity that atoms have for electrons. That's a fancy word, affinity. It means the greediness that certain atoms have for certain electrons. If you look up the electronegativity, right, so I'm going to list electronegativities. In fact, I'm going to display an electronegativity periodic table that will show you the electronegativities and the patterns of the electronegativities of all of the elements. And I'm displaying that table right now. And what you can see is that if you look on the left-hand side of the periodic table, there are weak electronegativities, and you go to the right-hand side, and there are strong electronegativities. And then, if you look very carefully, you can see where the halogens are: helium, neon, argon, krypton, xenon, and radon. And that's kind of a three-dimensional bar chart. And you can see their values are all 0. Why are they 0? They're 0 because they are the noble gases and their valence electron shell is filled up. So the noble gases do not want to get any electrons. They're happy with their 8 electrons in their valence shell. In fact, that's the reason why we call them the noble gases, because they don't react with any other elements. So when you're dealing with the noble gases, they all have electronegativities of 0. So that's an easy one to remember. You would have to be given electronegativity values. I don't think most professors would ever expect you to memorize them. But let's list the one for potassium. If you look up potassium in your book, or you could look it up on the web, the electronegativity number that you'll find most of the time should be 0.8 for potassium. That is a low electronegativity number. And if you look at the periodic table that I showed you, that makes sense because it's all the way over on the left-hand side of the periodic table, because potassium is a group 1 element. Now nitrogen is on the right-hand side of that electronegativity periodic table, and if you look up nitrogen's value, in fact you can see it on that table that I'm showing you, it is 3.0 for the electronegativity. So on the board I'm showing electronegativity values that I got from that periodic table. Potassium is 0.8 and nitrogen is 3.0. So what do these numbers mean? Remember, electronegativity is the affinity that the atoms have for electrons. So the bottom line is, the higher the number, the more greedy, or the higher the affinity that that atom has for electrons. So nitrogen really wants to grab everybody's electrons. He wants to steal electrons and keep them to himself. Potassium is the opposite. Potassium loves to give up his electron. And I'm going to display something else that shows you on an atomic scale 3 examples of non-polar, polar covalent, and ionic examples. And you can actually see what's happening between 2 different atoms and what electronegativities do. When you have a molecular formula like potassium nitride, all right, and you look up the electronegativity values, you have to know the delta En. Delta, whenever you use delta in engineering or science, that means the change or the difference. And this is the difference in electronegativities. And by the way, when you calculate this difference, you never get the convention is you never get a negative result. In fact, you could say that it is the absolute value of the difference to ensure that you don't get a negative result. So you take 3.0 in our case minus 0.8, and that gives you 2.2 for the delta En, or the difference in electronegativities. Now if you flip back to the, I'll flip back to the little electronegativity chart that I'll show you. You'll see on that chart I've got a region from 0 to 0.4, And that region is called the non-polar covalent bond. The region that goes from 0.4 to 2.0, including 0.4, is called the polar covalent bond situation. And then the region that goes from 2.0 out to, it says 3.3 here, but in fact it's anything greater than 2.0 is considered an ionic bond, including 2.0. In our case, our difference in electronegativity is 2.2. So the difference in electronegativity, now I also want to say one thing. The chart that I showed you is from a specific book. Those electronegativity difference charts vary depending upon what chemistry book you have. So get familiar with the one that's in your textbook. I'm showing you the one that I'm using. They're slightly different. For example, I have another text where it goes, instead of from 0 to, well, in fact, it matches up 0.4, and then it goes 2.0. But the other one I'm using goes from 0 to 0.5, and then from 0.5 to 1.7 instead of 0.4 to 2.0. So be familiar with the one in your textbook, because hopefully that should be the one that your professor uses. All right, so what does this really mean? And how does this apply to the Lewis structures? Well, the difference in electronegativity gives me 2.2. If we look at the chart, then now I know that anything from 2.0 on in that chart, 2.0 on, is an ionic bond. Ionic bond. It's an ionic bond. So the bottom line is I can say that potassium nitride is an ionic bond. So this is physically what happens. Nitrogen is so greedy for those electrons, and potassium doesn't really care about the electron it has, because its electronegativity is only 0.8. Potassium is willing to give it up. Nitrogen wants to grab it up. So what happens is this electron and this electron, it forms a bond between these two atoms. In fact, if you have another potassium floating around with one electron in its outer valence shell, this guy is going to form a bond with this guy, all right? And then if I have another potassium over here with one electron, he's going to form a bond like this. Remember those green boxes I showed you? The rule of the green boxes is that no more than 2 electrons can occupy those green boxes. And in fact, we can extend that rule to this kind of bond, because when I draw the line like this, you can assume we have 2 here. When I draw the line like this, you can assume we have 2 here. When I draw this bond, we have 2. So now, nitrogen is actually happy because he's got 1, 2, 3, 4, 5, 6, 7, 8 electrons in its outermost shell. There's something called the octet rule of bonding that you must know for chemistry. The octet rule for bonding. It basically says that all elements on the periodic table are in their happiest state when they have a full outer valence shell, and most of the time it's 8 electrons. Why do I say most of the time? Because there are 2 exceptions if you look at the periodic tables. Those 2 exceptions are hydrogen and helium. Hydrogen is happiest when he has 2 electrons in his outer valence shell. Helium, the same thing. The rest of the elements, from lithium all the way down to lawrencium, the rest of the 116 elements, are happiest when they have 8 electrons in their outermost shell. Nitrogen is closest to neon. So we say that nitrogen wants to get the outer valence shell with 8 electrons that's closest to its noble gas, neon. And there's a rule in chemistry that says basically that's what all elements want to do. They want to get the same number of electrons with their nearest noble gas neighbor. So look at the periodic table, find out where the nearest, as you go across the periods, you're reading from left to right, just like you do in English language. And you read from left to right, go down a line, start over on the left, go to the right. The same way that you're reading a book is the way you read the periodic table. When you go from left to right, you're going across groups, but you're in the same period. So you go from left to right, and when you go from left to right from nitrogen, the next noble gas that you'll find is neon. So nitrogen wants to have the outer valence electron configuration of neon. So why do we say all this? We say all this because if you count up the number of atoms of potassium, look at this. We've got 3 of them. We have 1 nitrogen. So this explains why we have K3N. It's because the electronegativity, and now you don't have to know all of this for the Lewis structures, okay? What you have to know is you have to know the outer valence shell number of electrons for each of the elements, and then that helps you put them together. Now, this is not a structural formula. I wanted to show you the structural formula. The structural formula would look like this. I would have N with his 2 electrons over here, and then I would have a K like this, and a K like this, and a K like this. So this right here, this right here is a molecular formula. This right here is a structural formula. For the same thing, for potassium nitride. Why do we have these 2 different types of formulas? Why don't we just have one? Well, sometimes it's convenient to use the molecular formula because sometimes you're not interested in the structure of the molecule, you're only interested in the constituent quantities. You're interested in how much potassium, how much nitrogen is in that molecule. Other times, when you perform chemistry, it becomes critical to know what the structural formula is, because believe it or not, depending upon the structure of the molecule, it'll have different chemical properties. Now, the structural formula is not to be confused with the Lewis structures. The Lewis structures are just the element with its valence electrons around it. This is the structural formula for a molecule. And you'll have very complicated structural formulas when you study organic chemistry. The basic rules for the structural formula are that all of the bonds are at right angles with respect to each other. Are the bonds in potassium nitride, in fact, at right angles with respect to each other? No, they're not. There's another model that we'll talk about later that shows the real physical angles between these, and it's a 3-dimensional model, but that's not that. This is the structural formula. Why do we have a structural formula? Because this shows the structure in a 2-dimensional space on the paper. So we have the structure of the molecule set up like this that we're able to represent in the 2-dimensional space of the paper. And this is the structural formula for potassium nitride.